Okay, so hello everybody. Thank you very much for the opportunity to give a talk at this online conference, and thank you very much the organizers for putting this conference together. So today I'm going to stop. I'm going to talk about backward Bessel processes as an application to SLE. So this is a joint work with Professor Dmitry Belyaev and Professor Terry Lyons. So I'm gonna start by introducing SLE, that stands for Schramm-Loewner evolution, and after that I'm gonna discuss an application from backward Bessel SDEs for this SLE theory, and in particular we're gonna obtain some new structural information about the backward SLE traces. But first, let me with introducing SLE theory. So in general, we have a non-self-crossing curve in the upper half plane. Let's say this gamma t that starts from 0 and heads up to infinity. We consider a simply connected domain that is this complement of the curve that you can spot here. And the map GT has the property that it removes conformally this defect. Imagine that you have the upper half plane from which you have a cut, and this complement of the curve is a simply connected domain that you remove with this map GT in a conformal manner. And you see this index T here stands for time, and this, let's imagine that this cut grows in time as well, and then this maps GT for each time, remove conformally this thing, such that UT is the point where this tip, this green part of the curve, this green dot on the curve is mapped on the real line. Okay, so what we know from Riemann mapping theorem that there is actually a 3 real parameter family of these maps, and we would like to work with a unique map, and in this manner we establish a certain normalization at infinity called where we establish the behavior of certain coefficients in the Laurent expansion near infinity. And this we can talk about a unique map. So Loewner evolution encodes the dependence between this evolution of curves and the evolution of maps. And the precise dynamics actually written by Loewner is in the following differential equation. So I'll have an equation in the space of conformal maps where this UT is exactly where these curves are actually where these tips of the curves are mapped to the real line. So a priori UT is a real valued function. So far we started from a geometry, from a geometrical viewpoint, and we are moving towards, and we obtain this differential equation. Right now, I'd like to change a little the perspective and start directly with this differential equation. It has this forward Loewner differential equation, where this UT for the moment is just a real valid function. And I would like to put a random function there. And in order for this to output, and I will have somehow to, first of all, to reconstruct this curve, this gamma t. And as you can see here in this image, if I want to reconstruct this gamma t, I'm looking in this target space of this map GT. I'm taking the inverse in Z of this map, and I'm evaluating here. I'm shifting this green point such that is at 0. So I'm doing a horizontal shift, and after that I define this as a limit when the imaginary on the imaginary direction approaching 0, and with this procedure I construct backwards somehow these curves, right? And basically this is a definition of this trace gamma t. And in the case of SLE, actually what is SLE is a choice, is a particular choice of this UT, of this random UT that is square root of kappa Brownian motion. And this choice is actually motivated by models of statistical physics. This was introduced by Schramm around 2000. So basically what I called SLE is capturing the following definition, is that BT is a real standard Brownian motion, so it's a Brownian motion on the real line. The chordal SLE is defined as the lone curves induced by the solution to this differential equation where I did this UT being square root of kappa BT. So far I was focusing on this forward Loewner differential equation. Throughout the talk, actually, I'm going to work more with this HT maps. So GT maps were the maps that removed conformally this defect from the upper half plane back to the upper half plane, the canonical domain. These HT maps are the reversing time, dynamics. So basically, this is it. You can think about the maps GTZ as functions of T and Z, and these HT maps are the inverse in T of these maps, not the inverse in Z. The inverse in T. So it's really the dynamics is done in the movie is run backwards. Okay, so when I'm reshifting this, I'm just essentially here I'm just doing this identification, square root ht of z minus square root of kappa bt, that I choose for this ut. I'm just rewriting this equation here in the right as this dynamic. So as you can see, this looks like a complex Bessel process in some sense. So what I'm going to do, I'm going to do a standard thing. I'm going to extend this conformal maps to the real line and see what's happening. And the main thing that we can observe is that after some reshifting, after some dividing with kappa, as you can see, kappa was here before and right now is in this drift part. After this type of splitting with kappa, we obtain on the real line a Bessel process, as I said, but with a certain dimension that depends on kappa. So because the general definition of Bessel process here would be d minus 1 over 2, in order to relate this with the parameter kappa that appears as d of kappa is 1 minus 4 over kappa. So what is this interesting? Because here we work with a different family of processes, of Bessel process than in the typical SLE literature, is that here we have a phase transition in kappa at 4, like it's expected, but in terms of the behavior of this process. So the dimension is greater or small or equal than 0 for kappa less or equal than 4, and moreover, this process on the real line is absorbing. The origin has an absorbing behavior for this process, and for kappa greater than 4, the origin is reflected. So imagine that on the real line, this process, when it touches here, it starts to actually has also the possibility to go out, to exit. And of course, here you can ask you can ask a series of questions around this topic. For example, you can talk about the conformal welding homeomorphism if this is continuous in kappa. And this is this we answered together with Dmitry Belyaev and Atul Shekar in this preprint on ArcSafe that you can find. I prefer to not talk too much about this topic for the interest of time, but I'm happy to answer any questions if there are any. I'm going to focus more on this rough parts aspect somehow of the story. I would like to understand this differential equation as a rough differential equation. So the main problem with this equation, if you want, is that, as you remember, I'm interested when this Z0 is very, very close. If I would go back to the original formulation with ZT being complex valued, I'm very interested when this Z0 is close to the origin or really approaching the origin. So, and then this differential equation has a singularity here. So if you try to understand this as a differential equation, then this has really a singularity at Z0. But however, can we really understand the existence, uniqueness, non-uniqueness properties of the solutions, and can we get some new information on this dynamics? And this is actually answered in this preprint on ArcSafe that is gonna be the topic of the talk from now on. And there is an update of this result on my website. It's called Update PDF. The paper is called A New Approach to SLE Phase Transition, and you can find the update there. I'm going to talk a little, I'm going to give you the main result and some consequences. So what is the main result? The main result says that for kappa between 0 and 4, and for all times in a compact interval, there is a unique complex solution of the backward Loewner equation, started from the origin almost surely. For kappa greater than 4, there are at least 2 real solutions. So we talk about a non-uniqueness in the regime kappa being greater than 4 when you start this equation from the origin. And moreover, we obtain the following application. So when you consider a positive real number m for kappa from 4 to infinity, at the end of m macroscopic excursions, so these are excursions of length at least m from the origin of the squared Bessel process, we obtain an m macroscopic double point that is a double point of the curve of the SLE trace happening after time at least m. So we get a characterization of this double point of this family, of this subset of double points in terms of these excursions. And moreover, once you have these excursions on the real line of the Bessel process, you can also understand, because we have a lot of information about these Bessel processes on the real line, we're going to have also an understanding of the maximum of the process. We have a complete law for this. We have a closed form expression for the maximum. And this somehow you can imagine. This is the SLE trace starting from the origin at some point when the Bessel process starts a macroscopic excursion. Because you have a unique solution from 0, it means that the curve is actually also sliding on the real line, right? So the curve is growing in the upper half plane, but on this time of macroscopic excursion, it's sliding on the real line. So on this macroscopic excursion, using a lot of properties of the Bessel, you can understand the maximum, you can understand the asymptotics as kappa goes to 4 from above, so how these excursions really shrink. what is the intersection of this. More details in the paper. I'm just going to give you somehow an overview of this. So the key point is that you have this low dimensional information, test excursions of the Bessel that get you the dynamics of the curve. And the corollary is that almost sure properties of the trace given by the behavior of the Bessel of the origin. This is related with a question that Professor Peter Fritz asked me at the conference. So a very brief overview of what's happening. We have an existence story. You can prove it by taking z going to z squared and applying the standard dominated convergence theorem. Uniqueness follows from the absorption of the origin. Basically, this is the only possibility is to start this equation from the origin. Non-uniqueness, given phi, strong solution, construct an additional strong solution. And the applications, as I mentioned, are in the excursions of this Bessel. And we can get this closed form expression for the maximum, and this asymptote, this is very new. So this is the dimension that is 1 minus 4 over kappa in our context. And this tells you somehow how the maximum, how this trace intersections with the real line on this family of double points shrinks as kappa goes to 4 from above. So what is really this dynamics? And this, you can see that this is really a standard exponential random variable, where this MD is the maximum of the Bessel process on the real line. Thank you very much for the attention, and stay safe, everybody.